Jai Hind students, welcome to my YouTube channel. Students, I will start this session with the saying that it's not about being the best. It is about being better than you were yesterday. I repeat students, it's not about being the best. It is about being better than you were yesterday. So basically, the essence of these statements is that never ever be stagnant. Keep improving. There is absolutely always a scope for improvement in one's life. So students, keep progressing. So with that note, let's start today's session. Today we are going to derive the expression for the torque experienced by a magnetic dipole under the influence of uniform magnetic field, and then we will also try to find an expression for the potential energy stored in a magnetic dipole under the influence of magnetic field. So students, let's begin with the first expression. We need to find out the expression for the torque experienced by a magnetic dipole under the influence of uniform magnetic field, right? Uniform magnetic field. Diagrammatically, uniform magnetic field in a region may be represented by equidistant parallel lines like this. Suppose this is the uniform magnetic field. It obviously will be represented by a set of equidistant parallel lines like this. It is a region of uniform magnetic field, right? Okay, let us consider a magnetic dipole. Magnetic dipole means any fundamental arrangement comprising of north and south pole, equal and opposite poles. It's a bar magnet or any magnet. It can be termed as a magnetic dipole, isn't it? So suppose the magnetic dipole is placed under the influence of this uniform magnetic field. Let us represent the bar magnet like this. Let us consider this to be the center of the bar magnet, center of the dipole. And suppose this is the axis of the magnet. Let us consider this to be the axis of the magnet. Now, as you are aware, students, poles always exist in equal and opposite pairs. So let us represent this to be the south pole. And you will also remember, poles are not exactly the end points of a bar magnet, but actually these are the preferred regions near the ends of a bar magnet, where the magnetic force of attraction is maximum. So this is suppose south pole, and let us consider this to be the north pole. So they are of equal strength but opposite nature. So pole strength, we have denoted north pole, its strength by +N, and the strength of the south pole may be denoted by -M. Clear, students? And this is the direction of the magnetic moment. You must be aware, magnetic moment is a vector quantity directed from south to north. This is the direction of magnetic moment. For a dipole, the magnetic moment is defined as the product of magnitude of either of the pole strength and the distance between them. So the distance between south and north is considered to be 2L. So this is L and this is L. So total magnetic length is 2L, right? So students, magnetic moment, it will be given by product of the magnitude of either of the pole strength and the distance between them, which is the magnetic length. So it's a vector quantity and is directed from south to north. This we are already aware of, right? Now, very basic fact is that we have defined magnetic field, isn't it? Magnetic field actually is defined as the magnetic force experienced per unit pole placed at a point. This is the pole strength. So magnetic field at a point is defined as the magnetic force experienced per unit pole strength placed at that point, isn't it? So what about the magnetic force then? It will be M into B, right? This is the formula which we will be using. M is the pole strength, B stands for the magnetic field. This is the magnetic field due to some other source, isn't it? And these are the poles strengths plus m and plus minus m under the influence of this magnetic field. Now, as you are aware, magnetic field is a vector quantity, so it will be represented like this. Point I am making is, students, north pole, because it is plus m. So, north pole will experience a force mb along the direction of the magnetic field. While for south pole, its nature is opposite, minus m. So, for south pole, it will be F equals to minus mb, which suggests that south pole will experience a force mb in a direction opposite to that of the magnetic field. Clear, students? So, for north pole, F vector, it will be equal to mb vector. So, it will experience force along the direction of the magnetic field. This is the direction of the magnetic field. So, this is where it will experience the magnetic force. It is mb. Clear, students? This is the force experienced by the north pole under the influence of this magnetic field. For south pole, let's consider for south pole. The force experienced by the south pole would be minus mb vector. This negative sign suggests that south pole experiences a magnetic force in a direction opposite to that of the magnetic field. So, students, this is the direction of the magnetic field. So, it will experience a force in the opposite direction like this. Equal in magnitude but in the opposite direction. This is mb vector. Clear, students? Okay. Now, look. These are the two forces which are equal in magnitude, oppositely directed, and most importantly, they are having different lines of action. This force is acting along this line, and this force is acting along this line. So they are anti-parallel. So whenever the two forces are equal in magnitude, oppositely directed, and having different lines of action, then they constitute a torque, which will tend to rotate this dipole about point O in the clockwise direction, like this. Due to this torque, this dipole will tend to align along the direction of the magnetic field. Clear, students? So our objective is to find out the expression for that torque. And torque, we all are aware, it's given by the product of magnitude of either of these two forces and the perpendicular distance between them. So these are the two lines of action. So drop a perpendicular from here. So let us consider this to be D. Now, students, torque in magnitude, it will be given by product of magnitude of either of the force multiplied by the perpendicular distance between them. So this is how we are going to get the expression for the torque. So let's substitute the value. So what we get in magnitude, torque would be given by magnitude of either of the force. It's small n, which is the pole strength, multiplied by the strength of the magnetic field. What is the perpendicular distance with them? That's small d. Clear? Now, we need to represent this small d in terms of the magnetic length. So what do we do? Suppose, students, at point O, this is the magnetic moment and this is the magnetic field. Let us consider the dipole, this magnetic dipole, to be making an angle theta with the direction of the magnetic field. So theta is the angle which the magnetic moment of the dipole makes with the magnetic field, right? So since these two lines are parallel, therefore this angle would be also theta, pair of corresponding angles. Now this becomes a right angled triangle, right? This is a right angled triangle. If you consider sine theta, it is a right angled triangle. Consider sine theta, it's perpendicular by hypotenuse. Perpendicular is D. Hypotenuse is the distance from south pole to north pole, which is the magnetic length. Isn't it? So, small n, B, in place of D, we can write 2L sine theta. Clear, students? So, torque, it will be equal to m into 2L. it will give us the magnetic moment of the dipole under consideration. So we get N B sin theta. So students, this is the magnitude of the torque experienced by the magnetic dipole under the influence of uniform magnetic field. If you remember, it's the same formula which we have obtained in the case of torque experienced by a current carrying coil under the influence of magnetic field, isn't it? It's the same formula. The only difference is that in the case of current carrying coil, capital M stands for the magnetic moment of the current carrying coil, which is equal to the product of ampere turns and the area of the loop under consideration. In this case, it is the magnetic moment of the magnetic dipole of a bar magnet, which is product of the pole strength and the distance between them, which is the magnetic length. So this is the magnitude. Now students, in the vector form, torque, as you are aware, it's a vector quantity, and theta, it's the angle between M and B. Theta is the angle which the magnetic moment of the dipole makes with the magnetic field. So sin theta, so it can be represented by the cross product. It is M vector cross B vector. So this is the representation of torque in the vector form. This is the cross or the vector product, right? And by using the properties of vector product, we can safely conclude that tau is perpendicular to both M vector as well as it is perpendicular to B vector. So it is perpendicular to the plane containing M vector as well as B vector. And students, as you are aware, its direction would be given by right hand rule, right hand thumb rule, isn't it? So what do you do? Angle is to vary from M to B, like this. The orientation is from M to B, like this, in the clockwise direction. M to B. So my fingers should curl along the direction of orientation of the angle. In such a case, the thumb must represent the direction of torque. So the direction of torque is perpendicular to the plane containing M vector and B vector and directed inwards. So tau is perpendicular to both M vector as well as B vector, or torque is perpendicular to the plane containing M vector and B vector and directed inwards. And it is directed inwards. Clear, students? So this is the magnitude and this is the torque in the vector form, right? Now let's discuss some special cases. Now look, students, first case, if theta is equal to 0 degree or theta is equal to 180 degree. Look, suppose this is a bar magnet, this cap, black cap represents north pole and the other end represents south pole, right? It is placed under the influence of magnetic field like this. It is placed along the direction of the magnetic field so that the angle theta becomes 0, right? If angle theta is 0, then sin 0 is 0, so torque would be 0. Also students, if the dipole is placed like this is the direction of magnetic moment and this is the direction of magnetic field. So what's the angle between magnetic moment and the magnetic field? It's 180 degree. That's here. This is the case which we are discussing. So sin 0 is also 0, sin 180 degree is also 0. So since sin 0 is equal to sin 180 degree is equal to 0, therefore tau would be equal to 0. So students, what's the conclusion? If the dipole is placed along the direction of the magnetic field or the dipole is placed in a direction opposite to that of the magnetic field, in both the cases, it will not experience any torque. The torque experienced in that case would be 0, right? Okay, now let's consider the condition in which the dipole will experience maximum torque. So let's find out the condition for the dipole to experience maximum torque, right? So let's consider case 2. If theta is equal to 90 degree, then Sine 90 would be 1, which is the maximum value of sine function. Then tau is equal to tau max. So expression for tau max is mb. Sine theta, sine 90 will become 1. So this is the expression for the maximum torque experienced by a magnetic dipole. And what's the condition for the dipole to experience maximum torque? It will be experiencing maximum torque when the dipole is placed like this. Its orientation is like this. That is, when the dipole is placed perpendicular to the direction of the magnetic field, then this dipole will experience maximum torque. And maximum torque is mv. Clear, students? I hope it's pretty clear, right? Another thing, students, by using this expression, we can define magnetic moment as well. Look, this is the formula, right? This is the magnitude of the torque. It is mb sine theta. We need to define m. How to do it? Let theta is equal to 90 degree, so that sine 90 becomes 1. Also, let b equals to 1 unit. In SI, suppose it is 1 Tesla. So substitute these values over here. What do you get? Tau is equal to m, b is 1 unit, and over here sine 90. Sine 90 will be 1. Therefore, m would be equal to tau. So students, this mathematical expression can be used so as to define the magnetic moment of a dipole. So how to define it? This is magnetic moment. The magnetic moment of a dipole is numerically equal to the torque experienced by the dipole when placed at right angle under the influence of magnetic field of 1 Tesla. Clear? Should I repeat? Okay, I am repeating once again. The magnetic moment of a dipole is numerically equal to the torque experienced by the dipole when placed at right angle under the influence of magnetic field of 1 Tesla. So this is how the magnetic moment can be easily defined. Clear? Okay, students. Now since we have covered this particular topic, now let's proceed further. Now what we'll do is, we will try to find an expression for the potential energy stored in the magnetic dipole. Right? It is basically the extension of the previous topic. Now what we have discussed previously is the torque experienced by a magnetic dipole under the influence of uniform magnetic field is given by mb sine theta. Always remember, friends, theta is the angle which the magnetic moment of the dipole makes with the magnetic field. And this torque, it will tend to rotate this dipole in the clockwise direction, that is along the direction of the magnetic field, isn't it? Now students, imagine if I intend to rotate this dipole in the anti-clockwise direction against this torque, then definitely I have to do some work against this torque. That work done will get stored in the dipole in the form of its potential energy, perfectly in accordance with the work energy theorem. Again I repeat, students, if I intend to rotate this dipole against this torque in the anti-clockwise direction, say through a very small angle d theta, then I need to do some work. That work done will get stored in the dipole in the form of its potential energy, right? So, small work done in rotating the dipole through small angle d theta against this torque would be given by small amount of work done, dw, and in rotational motion work done is tau d theta. D theta is the angular displacement and this is torque, isn't it? So, what we get is, let's substitute the value over here. So, it would be equal to tau, it is mb B sin theta d theta. So total work done. Let us assume this dipole is to be rotated from initial angle theta 1 to final angle theta 2. Then total work done, it will be integration of dw taking suitable limits, which is theta 1 to theta 2. So the terms which are constant can be taken outside the integration. So it will be like this, theta 1 to theta 2. Now integration of sin theta, it's minus cos theta, isn't it? So what we get is, work done, it will be equal to mb minus cos theta, theta 1 to theta 2. Now this minus sign can be eliminated if I interchange the limits. Suppose this is theta 2 and this becomes theta 1. Now upper limit minus lower limit. So what we get is mb upper limit, which is cos theta 1 minus cos theta 2. So this is the total amount of work which is required to be done in rotating this magnetic dipole from initial angle theta 1 to final angle theta 2 under the influence of this uniform magnetic field. And students, this work done will get stored in the dipole in the form of its potential energy, right? Let us represent the potential energy by U. So what do you get? It is mb cos theta 1 minus cos theta 2. So this is the expression for the potential energy. It's pretty simple. Clear? Now we need to discuss some very important cases. Case of stable equilibrium, case of unstable equilibrium. So let's discuss the special cases now. Let us imagine the dipole to be initially making an angle of 90 degree with the direction of the magnetic field. So in that case, theta 1 will be is equal to 90 degree, and we rotate the dipole so that finally it makes angle theta with the magnetic field. So this is a special case. So let theta 1 is equal to 90 degree, right? Let us consider theta 1 to be equal to 90 degree. That is, initially we are considering the dipole to be placed like this, perpendicular to the direction of the magnetic field. Theta 1 is the initial angle which the dipole is making with the magnetic field. And when we rotate the dipole, either clockwise or anti-clockwise, suppose the final angle which it makes with the magnetic field is theta, say. Then work done or potential energy in such a case, it will be given by mb cos theta 1 is 90, which will become 0, minus cos theta 2 is theta. So cos 90 is 0. So what do you get? Potential energy is equal to minus mb cos theta. Clear, students? So theta, as you are aware, is the angle between m and b. So it can be represented as the dot or the scalar product of m vector and b vector. So u is equal to minus m vector dot, this is scalar product, b vector. Now as you are aware, students, the dot or the scalar product of two vectors is always a scalar quantity. We are aware, work done, potential energy or any form of energy, these are all scalar quantities, right? So this is the representation in form of scalar product. Now there are some sub cases. Okay, when theta is equal to 0 degree, let us consider theta is equal to 0 degree, then u would be equal to minus mb cos theta. In case the substitute value of theta is 0 over here, cos 0 is 1. So we get minus mb. This is the minimum potential energy which the dipole can possess. And students, you must remember a very basic fact that whenever a system possesses minimum potential energy, then it corresponds to the state of stable equilibrium. So, it corresponds to the state of stable equilibrium. Clear, students? So, what is the orientation of the dipole for attaining the state of stable equilibrium? It should be like this. This is the magnetic field, and the dipole should be placed like this. This should be the north pole and this should be the south pole. So like this. So what's the angle between M vector and B vector? It is 0 degree. It is in this case that the dipole possesses minimum potential energy. And this is the state which corresponds to the state of stable equilibrium. Clear, students? So, whenever the magnetic dipole is aligned along the direction of the magnetic field, then potential energy possessed by it is minimum and it is the case of stable equilibrium. Now let's consider the other subcase. When theta is equal to, suppose 180 degree. Now students, cos 180 degree, as you are aware, is equal to -1. Therefore, in such a case, the potential energy of the system will be cos 180 degrees -1, minus minus get cancelled. So in that case, we will get plus mb. And this is the maximum potential energy which the magnetic dipole can possess. And whenever the system possesses maximum potential energy, then that state corresponds to the state of unstable equilibrium, right? So it is the condition for unstable equilibrium. So what will be the orientation of the magnet in this case? It will be like this. This is the magnetic field and the dipole must be placed in this manner. This must be the south pole and this must be the north pole, so that the direction of the magnetic moment is like this, opposite to that of the magnetic field. So here the angle theta, which is the angle between the magnetic moment and the magnetic field, must be 180 degree. So this orientation, when the magnet is placed parallel to the direction of the magnetic field, it corresponds to the stable equilibrium where its potential energy is minimum, and this orientation of the dipole, where it is placed in a direction opposite to that of the magnetic field, this represents unstable equilibrium where its potential energy is maximum. Clear, students? So students, I hope you have understood all these topics. They were pretty simple. Just compare it with the topics which we have discussed in electrostatics. Case of an electric dipole under the influence of uniform electric field. The expression for the potential energy of an electric dipole which is under the influence of uniform electric field. We have discussed all these cases there also. The only difference was, here we are considering the case of magnetic poles having pole strength plus and minus m. There in electrostatics we have considered the case of equal and opposite charges, plus q minus q. Here it's the case of magnetic field. There we have considered the case of electric field. So try to correlate these two topics. You will find much easier to remember all the formulas in magnetism. Clear, students? So that's it for this particular session. Do join me in my next lecture then. Till then, bye bye, and do take very good care of yourself. Thank you.